So let's talk about an example of a charge moving in a magnetic field. I want to take a little divergence from the idea of even a conductor. What if we go back to this idea of the cathode ray tube and we put a magnet where we can fire an electron through a magnetic field in a cathode ray tube? So if I fired a charge between two magnets that I put around a north magnet and a south end of a magnet, around a cathode ray tube electron firing gun, I could fire an electron between these two magnets. So we call it Q. And this Q subscript E, would have a charge of negative 1.6 times 10 to the power of, what is it, negative 19? Is that right?
Yes.
Negative 19 coulombs. And we could talk about having a velocity. Let's say that based on our previous calculations, we were able to get an electron up to a speed of 8.0 times 10 to the power of 4 meters per second. Pretty healthy speed. And let's say that the intensity of the B field that these magnets are able to produce, that we're able to somehow wrap around our television tube. Yeah?
Do we have the equation to find the B field?
Not yet. That's where we're going next. Let's say that the B field intensity is equal to 0.30 Tesla. And you know what? Let's say that the little kid that's trying to break this television using magnets doesn't get the magnetic field perfectly perpendicular to the path of the charges, but maybe makes it so that the angle between the magnetic field orientation and the actual path of a fired charge within our cathode ray tube is... It's like an overhead view. Let's make it an overhead view.
How do you decide which angle?
Yeah, which might be
Sorry. Oh, if the magnetic field is going this way, and the charge is going off in that direction, then the magnetic field would be the angle between those two.
But wouldn't that be?
The same value. They're parallel.
You want to talk F patterns and opposite angle theorem?
What about not that one?
No, the other.
Oh, this one here?
180 minus beta.
Oh, true, yeah.
Never mind.
Yeah.
The value's still the same.
Yeah, so we can follow the cast rule if you like, but it's the same value you're going to get in the end. Okay. All right, so what you get for the theta is 50 degrees, let's say, by observation. Okay. Let's figure out what the force would be acting on this electron. So the formula we said previously was that force is equal to QVB sine theta. And this is an important point that when we're talking about cathode ray tubes, we often talk about V and delta V, like V for velocity with an arrow. Try to keep your V's lowercase v. You should do that anyway and put an arrow over top of them just to really illustrate that this is a velocity, not a voltage difference like we've been talking about in some previous examples. And again, we can put in the sign on the charge, but we know that we're really just looking for a magnitude of force here. 1.6 times 10 to the power of negative 19 coulombs.
Negative 1.
Yeah, I put negative. I didn't see it. Times velocity times field intensity times sine of 50 degrees. Maybe I should have dropped my units just so I could fit it in there. Yeah.
So even though you're saying that like A and B are vectors,
Mm-hmm.
and it doesn't matter what direction they're in because you're taking this.
Yeah, the sine theta is a part. Well, I don't want to do a lesson on cross products, so for now we're just going to treat this as a formula, okay? But when you get to math, and this is the frustrating thing sometimes about learning things in parallel, like between two courses, this is a cross product of these two vectors. We talk about dot products, and you notice at the end of a dot product there's a cosine theta. So when you get to your calculus course where you're talking about multiplying vectors, there's two ways to multiply vectors. One's called a dot product, and it gives you a scalar result. And one's a cross product, and it gives you a vector result.
Okay, so but like when we're doing this calculation, we don't
No, just the magnitudes. Yeah, and the theta accommodates for the direction. Okay? Or the relative direction. Okay, somebody that's quick on the buttons with the calculator. What do you get for the force? Negative 2.9 times 10 to the 23 newtons. Now the negative isn't something we're so worried about. We're really just concerned about the magnitude here. So 2.9 times 10 to the power of 23. Now if this is an overhead view,
I got like 1.0075 times.
oh, we have some democracy.
Like 2.9 times 10 to the negative 50.
Me too, yeah, that's what I got.
2.94 times 10 to the negative 15.
Uh-oh.
Did you do a negative 4 instead of, did you do 8.0 times 10 to the negative 4?
I didn't do anything. You guys helped me.
Everyone versus Tyler again? No, Tyler is negative 1.6 times 10 to the 19.
Oh, use positive 19. Oh.
Are you sure?
Well, a negative exponent on the 10 makes more sense because the
Yeah,
negative
I got
19. So.
1.0075 times 10 to the negative 15.
Okay. Well, I'll pull out my calculator. Let's see.
Now let's try Tyler's.
1.6 times 10 to the power of negative 19
Yeah, Tyler, you definitely
times
forgot
8
negative. If you forget that
times
negative, you get
10
your
to the
answer.
power of 4 times 0.3 times sine of 50 equals 2.94 times 10 to the negative
Are you
15.
putting everything in brackets?
Well, it's all multiplication, so it doesn't need to be.
I got 2.94 times 10 to the negative.
Yeah. Okay, so 2.94 times 10 to the power of negative 15, or sig figs would be,
Wait, hold it, it's negative.
yeah, negative, okay. 9 times 10 to the power of negative 15. The fact is we're not too concerned about the fact that it is negative because what we really care about is the magnitude of the force, and we're going to rely on our right-hand rule. So let's focus on the right-hand rule for a second for the direction
Oh, I'm in
because,
radians, that's why.
oh, radians makes sense, okay. So we're going to focus on the right-hand rule to talk about the direction, and I want to look at this as an overhead shot. So knowing the context that this is an overhead view, get your right hand out. You've got the magnetic field oriented in the direction of your fingers. You've got your thumb oriented in the direction of your wire. What direction is this getting forced?
Into the page.
Into the page. So we don't have a nice directional reference. Well, you could do a circle with an X. That would be an away from you arrow. Or you could say way. We don't have a nice directional reference frame yet for that. Yeah.